solutions called the colligative property of solutions. You're probably familiar with at least one colligative property, even though you don't know about it yet, and that is the reason we put salt and other chemicals on the roads when it snows. We say it's to melt the snow or to melt the ice. What it actually does is lowers the freezing point of the snow and the ice, so that when you lower the freezing point, the temperature now is higher than the freezing point, and that way the snow or the ice does melt. So first, a definition: a colligative property is any property of a solution that depends only on, we're going to say, the number of solute particles, but that's really what the concentration is telling us, how many solute particles there are present in the solution. It doesn't matter what the identity of the solute is. What does matter for colligative properties, and we'll see more about this in the next lesson, is what the solvent is. So there are three colligative properties we're going to talk about. There's a fourth one that's a little bit more complicated that we won't talk about, and it has to do with something called osmotic pressure. And if you're interested, I can let you know separately. But the first of the three properties we're going to talk about is vapor pressure lowering. So you lower the vapor pressure by putting a solute into the solution. Here's how that works. The solute in solution, so here's pure water on the left, and pure water, we have, as we remember back before, the vapor pressure happens when the rate of evaporation is equal to the rate of condensation. And if this is a closed system, so let's put a lid on this, then we build up that pressure where the two processes become equal in rate. And that's where we have the vapor pressure, the equilibrium vapor pressure. Now, what happens to the solution is that the solute blocks access of the solvent to the surface. So now here we have some sucrose here, but this could be anything. And what the sucrose does is it's going to block access so that molecules of water that otherwise would be able to get to the surface now are blocked. And the other thing it does, I don't have that in the diagram. The other thing that does is it does attract the water molecules, because we've got lots of H bonding going on here. And so the H bonding can attract the water molecules. And what it does is it reduces the rate of evaporation. So now the rate of evaporation goes down. Since the rate of the evaporation goes down, that means the vapor pressure also goes down until the rate of evaporation and the rate of condensation are again equal. So we've got a couple of things going on. Solvent-solute intermolecular forces can be stronger than the pure solvent, and so that lowers the rate of vaporization, decreases the vapor pressure, as I said. As the concentration increases, the number of particles goes up, and the rate of evaporation goes down even more. So higher concentration leads to a lower vapor pressure, and we can draw a little diagram. If we have the concentration on the x-axis and the vapor pressure on the y-axis, we're going to see a decrease. And I'm not sure if this is linear or some other function. The vapor pressure goes down as the concentration goes up. So this is the first of the colligative properties. The rest of them kind of follow from this one, which is why we cover this one first. So in this case, the vapor pressure goes down. And when the vapor pressure goes down, if you recall the definition of boiling point, the boiling point happens when the vapor pressure equals the atmospheric pressure. Well, if the rate of evaporation and the vapor pressure are going down, what we see on this phase diagram down below is that as the vapor pressure decreases, so come along this diagram, the red curve is the pure solvent, and that's both for the solid liquid interface here, so pure solvent here and here. Actually, let me use green. Now let me use red there since we've got red. So the pure solvent here and here, and then the solution is the green curve, and we'll talk about what's going on with that green curve in a moment. So essentially what's going on here is that at every temperature along the way, the vapor pressure comes down. So the vapor pressure is lower for the solution everywhere along this curve. So that when we get up to the original boiling point, so this is the original boiling point, the boiling point of the pure solvent, the vapor pressure is lower. It's not up to atmospheric pressure. And we need to get to a higher vapor pressure, a higher temperature out to here to get to the 1 atmosphere line. And so the boiling point of the solution goes up. And this is called boiling point elevation. As the concentration increases, the rate of the solvent solute intermolecular forces also increases. And so it's going to take more energy to form the bubbles. As we saw up above, we are going to see an attraction of the water molecules, decreasing the vapor pressure, attracting those water molecules, or any solvent, better. So in the case of water, the water and solute molecules that are on the surface are harder to evaporate, and so you need more energy. You need more energy to get to that evaporation. More energy means higher temperature. Remember kinetic molecular theory. Temperature measures the average kinetic energy. And this is actually governed by those same kinds of curves that we saw where there's enough particles above a certain energy to evaporate. And as we saw before, the greater the concentration, the greater the effect. I'm going to start having you think about that increasing concentration increases the effect, because we're going to see it's going to be tricky to keep track of whether the effect is making us go up or go down. But no matter what's happening, the greater the concentration, the effect, oops, 2 F's, not 2 E's. The effect is going to go up as the concentration goes up. And in the case of boiling point, as the concentration goes up, the boiling point is also going to go up. So what happens here, and this is going to be something that's going to be important to us in a few minutes, is that the solid and the liquid are both pure. So solid and liquid, solid and the gas, not the liquid, the solid and the gas are both pure. Now the liquid up here, this is a solution. And in order to get to the pure substance, either going from the liquid to the gas to evaporate, or from going from the liquid to the solid to freeze, we're going to need to basically push the solute molecules out of the way. So to go from the solution to the pure substance, the solute needs, I was right the first time, needs to be pushed aside. So that's going to tell us what's going on in terms of the conceptual reason for what happens to the freezing point. But let's take a look right now while we're here and see from a point of view of the phase diagram what's happening to the freezing point. So at 1 atmosphere pressure right here, that's our normal freezing point, the freezing point of the solvent. The triple point, that place where we're in equilibrium with all three phases, in order for the triple point to work out properly, the triple point slides down the solid vapor line. And so the triple point also goes down, which means at every pressure along here, the solid liquid interface moves to the left. And so the freezing point goes down. So the freezing point of the solution is lower than the freezing point of the pure liquid. All right, so let's take a look at what's going on a molecular point of view in freezing point depression. And this is what's going on when we put salt and other ice melt things onto the road. So on the left of this diagram, we have ice, pure ice, and we've got that familiar hexagonal structure of the water water molecules with their hydrogen bonding to their nearest neighbors. And recall that freezing requires formation of these strong intermolecular forces. Now, this freezing, formation of IMFs, this is an exothermic process. We have to remove energy to get that to happen. And what happens is the solute particles on the right, in this case, we're seeing some sodium chloride. So we got the large sodium, large chloride, the smaller sodium, is blocking that water molecule from getting into the ice. It's making it difficult to get into the ice. So it slows down the rate. The rate of freezing goes down. The rate of melting, though, doesn't change. The melting is not changing. This melting is still going on as fast as it was before. So the rate of melting stays the same. And what happens is we need to lower the temperature. What we're doing is lowering the temperature. This does a couple of things. It lowers the rate of melting, and it also removes more energy. So as we lower the kinetic energy, we're removing energy from the system. Now that removing energy, now the intermolecular forces that are attracting the water molecules to us, to the crystal, are strong enough. They can overcome those intermolecular forces, and they can get past and push those sodium and chloride ions. They're going to push those out of the way. In this case, again, as the concentration goes up, the effect goes up, but you got to be careful. What is the effect? The effect is that here's our concentration. The freezing point is going down. And one of the questions that a lot of people miss on this is here the concentration is 0. That's the pure liquid. So a pure liquid has the highest freezing point. And so those are some of the questions that we're going to ask you. So on the worksheet, you'll see some questions that are going to have that effect. Now, let's take a look at all three of those at once, and let's plot them all onto the same graph. Remember, the effect is increasing, but you've got to think about what is the effect. The vapor pressure is going down, vapor pressure lowering, boiling point elevation, and freezing point is going down. So notice that 2 of the 3 go opposite to what's going on with the actual concentration. So if we draw a graph of that, and we look at the boiling point, and we look at the freezing point, and we look at, I'll use a different color for this, we look at the vapor pressure. As the concentration goes up, the vapor pressure goes down, and the boiling point and the freezing point go in opposite directions. And actually, if you think about it, that's probably a good thing, because if you didn't have the freezing point and boiling point going in opposite directions, there could come a point where the 2 of them come together. And if the 2 of them came together, that would mean that you'd have to boil before you froze, and you get into all sorts of weird stuff going on there. So in this little exercise here, I'm going to ask you to look at 3 solutions. We got these 3 solutions: 1 molar potassium bromide, 2 molar potassium bromide, and 3 molar potassium bromide. And I want you to pause the video for a moment as you think about which has the highest vapor pressure and the lowest, which has the highest boiling point and the lowest, which has the highest freezing point and the lowest. Okay, so I hope you froze the video just a moment to think about it and wrote your answers in. So remember the effect. Vapor pressure, the higher the effect, is going, I'm sorry, I want that backwards, going down. So the bigger the effect, the lower the vapor pressure. So the 3 molar is going to have the highest, the lowest vapor pressure, and the 1 molar is going to have the lowest highest vapor pressure. I keep saying that backwards. The boiling point, the effect is to go up. So the highest boiling point is going to be solution number 3, the 3 molar, and the lowest one is going to be solution number 1, the 1 molar. And likewise, the effect for freezing point goes down, and so it's going to be like A, the 1 molar has the highest freezing point, and the 3 molar has the lowest freezing point. All right, at this point now, we've got a couple of demos to show you. You can go watch the demos right now. I've posted a video of my colleague, Mrs. Glynn, demonstrating both of these demos for you. And she gets quite excited. I had to make it private, though. She doesn't want to have it a public YouTube video, so you'll have to use the link that's there. And please don't share that link. At the same time, leave some nice comments. Tell her what a good job she's done so I can show her. And she sometimes needs a little ego boost. All right, so let's talk about the videos, talk about the demos. Let me tell you what the 2 demos are first, and then we'll talk about them. In the first demo, we're going to put some food coloring in ice. And let me change over to green, so that happens to be the color that we used. So we're going to put some food coloring into ice. And you know what? Let me change that again. Let's make a beaker. So we have a beaker here. And in that beaker, we've put a relatively dilute solution of water with some green food coloring in it. And we're going to put that into the freezer and think about what happens when you put things into the freezer. How do they freeze? If you've ever looked at an ice cube tray, maybe you've noticed that there are bubbles in the middle. Where did those bubbles come from? Why are there bubbles in the middle of the ice? And think about the freezing is going to happen from the outside in. Okay, that's the first demonstration, and I'll let you think about that for a few moments. In the second demonstration, we're going to take some club soda. So a bottle of club soda. Club soda is just seltzer water, and this is just CO2 dissolved in water. So the solute now is carbon dioxide gas. And before we open up the bottle, so let's see if I can draw a soda bottle. That's not too bad. Before we open up the bottle, so we have the cap on the bottle. Before we open up the bottle, there's a lot of carbon dioxide dissolved in here. So high concentration means that the freezing point is way, way down. And up above the carbon dioxide level here, we have about 5 atmospheres of carbon dioxide. So what do we have? We have a high solute concentration, and that means a low freezing point. And in fact, the freezing point is so low that we can get this down to a temperature of about -8 degrees Celsius, and it's still not frozen. So let me draw a little diagram. I like this diagram here because it kind of shows us what's going on. This is a diagram of temperature. And up here is 0 degrees. And what does 0 degrees represent? Think about that for a moment. And right now, the temperature of this solution is going to be at about -8 degrees. But because of the concentration of the solute in there, the freezing point is probably down around -10 to -12 degrees. By the way, this is all in degrees Celsius. Okay, so since the temperature is greater than the freezing point, we have a liquid. So think about for a moment what happens when we open that soda bottle. Okay, so you can pause the video now, pause this video now if you want, and go watch Mrs. Glynn's video, or just keep on watching here, and then you can go back and watch Mrs. Glynn's video at a later time. So coming back up to our food coloring in ice, and this is a wonderful demonstration. If you've seen the video now, it's kind of interesting to see. And I'll also post just a static JPEG, a picture, to show you what this looks like. So what's happened now is, here's our beaker. And here's the level of our water, but I'm not going to draw it with green, and you'll see why in a moment. When the water freezes, it freezes from the outside in. So it gets colder on the outside first, right? It gets colder all the way on the outside. So from the freezing occurs from the outside in. When you see ice cubes in the freezer, the gas that's accumulating in the middle happens because water dissolves gases. Remember, gases are slightly soluble in water. And so there's some concentration of oxygen and nitrogen in the water. And as it freezes, as the water freezes in your freezer, then that pushes, just like this, it's going to push those bubbles into the middle until those bubbles can no longer stay dissolved. Well, that's the same thing that happened with the food coloring. The food coloring got pushed into the middle until it was no longer able to stay frozen. And then eventually the food coloring all froze in the middle. And surrounding that food coloring, this was that pure ice, pure water. And that's what was going on when we saw in the phase diagram up above, that you make the solvent pure. And this is actually a way to purify solvents. If you can figure out a way to get them to freeze so that the solutes are pushed away, then you can purify solvents this way. That's a pretty cool trick to do. Meanwhile, what's going on with a soda bottle? So soda bottle, let's open up that soda bottle, just like Mrs. Glynn did. Open up the soda bottle. By the way, both of these are experiments that you could actually, oh boy, that's a pretty bad soda bottle. That was a fat soda bottle. That's a little bit better. Okay, so we've opened the soda bottle now. And so what's going on is the CO2 escapes. So the pressure of the CO2 now has dropped significantly. In fact, the 5 atmospheres of carbon dioxide before that was pure carbon dioxide. Now, the pressure of the carbon dioxide is really, really low. It's like 1 millimeter of mercury. I don't know, somewhere very, very small. So what has happened? What has happened is you saw bubbles forming. And so this concentration of the CO2 drops significantly, goes way, way down. What happens to the freezing point when the concentration of the carbon dioxide or the concentration of any solute goes down? Well, the freezing point goes up. Now, look at our diagram on the left in the middle here. Concentration, carbon dioxide goes down. By the way, we've got a couple of things going on here, so this is a little complicated, so I hope you're following. So now, the freezing point is going to come up, and it might come all the way up. I don't know. Maybe it comes all the way up to the regular freezing point, but there might be a little more carbon dioxide in there. So maybe we come up to, say, -1 degrees C as our freezing point. Now what happens? Well, now the freezing point, or the temperature now, is less than the freezing point. And since the temperature is less than the freezing point, it freezes. Now, it doesn't freeze completely. Remember, freezing is exothermic. It releases energy. So as the water freezes, it's also releasing energy, and that makes it so it's not going to freeze solid. It does keep some of the water liquid, and so we get slush. And that's our run at colligative properties, at least conceptual colligative properties. In the next lesson, we're going to learn about some calculations that we can do to figure out just how high or just how low the freezing points go, and to use this as a technique for measuring the molar mass. So now we have another technique we learned last unit, that you can use the density of gases to find the molar mass of the gases. And now we're going to use the freezing point depression and boiling point elevation. I am going to post one more video too of a more just straightforward freezing point depression with soda bottle. Unfortunately, the person titled the video freezing point elevation, so ignore that. It is freezing point depression. Okay, have a great rest of your day, and I look forward to seeing you again soon.